So what, you can't record it today?
Yes. Okay, so this week we're looking at recursion again, following on from induction last week. The section for reading starts on page 43, and the questions are on page 45.
So we're going to do question 5?
Yes, we are. We're going to, so... Oh, yes. Yes, we'll also do that as well. The questions for this week are going to be on page 45, and it's 1, 3, 5, 6, and 7. So if I can find it. Page 45, question 1, 3, 5, 6, and 7. Okay? It was the ancestor question, wasn't it? From last week. Yeah. We'll look at that.
Rings a bell. I can't remember last week very well. I can't remember what I did yesterday very well. Anyway, that's
Did anyone else look at question 5 from last week?
I wasn't here last week.
Okay. But you guys have looked at it. Is that right? You've looked at it. Have you got an answer? Yeah. So have you got an answer for 5?
No, I didn't actually.
Okay. We can talk through the answer a bit if you want this.
Yeah.
Relatively straightforward.
actually right this week.
Basically, it's saying.
Yeah, sir.
It's basically saying that we have a basis which says if A is a parent of B, then A is an ancestor of B. Yeah. So if A is a parent of B, then it's an ancestor and parent effectively. Same thing, yeah. And then the induction rule would be if A is a parent of X and X is an ancestor of B, then A is an ancestor of B.
Right.
And so then we keep on looping around to see whether X is an ancestor of B, X is an ancestor of B, to be able to go back whether it's kind of a grandparent or a great grandparent or.
Okay. Yeah.
So does that?
Yeah.
Do you see how that fits? Yeah. Excellent. times 2 plus r, where r equals 0 or 1, and m is n divided by 2. Yeah?
Yeah. Because the issue is, yeah.
But bear in mind it's integer division. That m.
Okay,
So-
yeah, because I thought it'll just be.
Yeah, no.
Okay,
So
okay.
for instance, if n was equal to 5, and it was 5 divided by 2,
Just 2.
it would be 2. It's probably makes more sense if you look at the function below,
Yeah.
where it says int m equals n divided by 2.
Yeah.
So it's because it's casting it to an int straight away. It's called that way.
Cheers.
Okay.
It's on here.
Highest level drawings you'll get to.
Well,
Unfortunately,
not drawings, but
you look good.
Wow.
as long as you can make that.
So there's a chance I should have
Why you must do
The same as me.
No, we've
It's the same right already. Intervention.
And that's the problem.
Last character's given the first character back to the last character.
Discussed it
It's
by
one in the middle.
myself and it's still good.
But it gets the middle. But it decides we want it doesn't matter if it
With
gets.
this, I can open.
So that's why it has to end.
I can look at it. But with
That's what
the
I'm
other
thinking.
stuff, I either just
There's no actual matching pair to make
jumble of notes which are.
If you had X, that's a power, but if you've got
As I say,
P and XP, then you get rid of the two P's, then
Like
you
keep it
just leave with X.
putting
What are you
it
gonna
in
do with that?
folders. Whereas with paper, it will just get lost. You never find it again.
My thoughts on this.
If it equals 0 or 1.
No, it's because I need to do this by
so now that you can does the idea of recursion make sense? How you get to the
Why it should terminate, or whether it does terminate.
It's asking why we want it to terminate.
Oh,
So if it's
I'll do that question too.
Yeah, absolutely. So no matter how long or short this string is, because you're always moving one from the start, one from the end, eventually it's going to get to a case where you've either got one single character, or if you start with a leading number, then no
So it's
characters,
looking through
which is where the terminating clause here comes in. So does that make sense?
Yeah.
Makes sense. Question 1. Does it make sense? Yeah.
Eventually, the character's not gonna match.
When you look at what the comments are, like alongside the lines of code. Yeah.
That's what we do with characters don't match.
Yeah.
So that's the stop
Well,
eventually.
that's the way of testing for pattern match, isn't it?
Basically, if they do equal it, they keep going.
Keep
It's not.
going. Yeah.
I'm getting my whole question. I'm doing question 3 now.
Further details of the following recursion now.
Yeah. So question
Very less than still, that's the one.
System outprint, you've got to do 0 or 1.
Well, think about what the variables should be in the blanks. You've got 3 blank spaces. Now, the points above are defining the rules for this.
So it'll be not all one, or not and one, might be like this. And
Yes.
greater than
Start
one,
and the end of the
should be
trace.
written as
Yeah.
n,
Then you'll know or if.
we reckon, and it's less than two, so it's greater than one, so it's less than two. It's less than just than two, it's not me writing it's an equal one.
So for every
So it's,
Okay, so it's less than two.
it makes something.
if you think about, think about the answer, you know that if n is less than 2, then you're going to be in this path, and you're going to want to print something else.
Basically, so if n is greater than one, it's not greater than two.
Well,
Yes.
that means I have to
Yeah.
go home.
Then it's going to print one or zero.
Right. Rather than thinking about this for a minute, just think about what this function is trying to achieve. So you give the function an integer.
So if
So
that
suppose,
number is less than two, print out whatever that number is, 0 or 1.
yeah. So
So
what?
print out basically print out.
Absolutely, yeah. Then if it's greater than 1, then it's going to, so 2 or
If m equals n divided by
it's
2.
going to end up in here. We've got m and we've got r as our variables in that set. So one of those variables
Then divided by 2.
we want to be able to recursively call something, and we also want to be able to print something. So think about that point 2, what this is saying about the function, and that might help you work out what should be in those brackets. Okay. Which question are you looking at? Okay. So, do you understand what the function is trying to do? Yeah. So, you've got this. It's been given an integer, and the idea is that we're going to print out the binary equivalent. So, one example would be if I gave it the value 5, it would print out 1, 0, 0, which would be the binary equivalent. Yeah. Taking a step back, if we gave it the value 1, then what would you print out? 1, exactly. So, if we look at this first part, if n is greater than, if n is less than, sorry, I can't read upside down. If n is less than 2, so in the case of 0 or 1, we're going to end up in this part of the function. Yeah. So, if it's 0 or 1, n is equal to 0 or 1, what do you think would print out? So if it was equal to, if n was equal to 1, what could we put in this bracket?
1.
Kind of, yes.
Sorry. Say it again.
If n was equal to 1,
Yeah.
what would you put in the bracket? We want to print out 1, but what's got a value of 1 at the moment?
First one.
So think in terms of variables rather than numbers.
Okay.
So what variable could we put in there?
N.
N, absolutely.
Right.
Because it could be 1 or it could be 0,
I said.
rather than putting the actual value in itself. Okay, so that in effect takes care of our base case. Yeah?
Yeah.
Where we start with that. So then, if we think about when we start with something greater than 1, then we're going to end up in this else statement. Yeah? And in the else part, what we do is take our value. So suppose we gave it 5 to start with. So n is equal to 5. Then we would say here, n divided by 2 to get a new value for m, and n modulus 2 to get a new value for r. So then, once we've got these two values m and r, we need to think what we might
Right, yeah,
want
so.
to recursively call the method with. So that would be what we recursively call the method there. So some value that would feed me back in as a new value of n, and also whether there is a value that we print out after the recursion.
Surely you're meant to be through.
Yeah, that's the final
So
state
is it,
of the remainder. We have to do, where it says like print bin and south, do we just keep going through the print bin before we, just
Yes.
out?
So if you think print bin is going to start you back in giving you a method, yeah.
So we don't print out anything.
So you haven't reached that print out. The only 2 points where you can print are here, and we know that we only print here when we're left 1 or 0, and here once we finish the recursive step.
Okay.
So effectively, a recursion is going to get you to get back to that line.
So we're pretty much printing backwards, forwards.
Kind of, yeah. But you're going all the way back until you get to this base case.
Okay. And then
And
we'll start
then
printing.
it will exit this function and allow it to continue onto that last line.
Okay. Yeah.
So with that in mind, what do you have any idea what the variables might be for those brackets?
I just tested it out.
That's the best thing to do.
Yeah,
So if you
so-
tested it out and you've got your M and you've got your R, and in fact the way you've written it is exactly how I'm going to write it.
Yeah.
What would you put in the brackets?
I thought it had a start.
Absolutely spot on.
I think it's best if we can go through the board.
Yeah, yeah,
It's easier to
Sure.
understand that way.
Yeah.
And modulus, is that the end you put in modulus to?
Yeah. I think. Yeah.
It does.
It's not the one you've
but
worked
it
out.
only
I
gets
was doing
to
a
that
modulus, I was doing
once
modulus of the
it's
one I worked out.
fully executed,
Like that
fully
one,
executed the function. And the only way to fully exit the function
So
is
0, 1.
effectively by doing
One
that
level
one.
0.
Because we can we will either end up here or we will end up here. If we end up here, we know we recurse. So the only way to terminate really is that line. So we will recurse all the way back to the base case, if you like. Then, effectively from there, we jump into the closing bracket, and so the function has terminated. So then it will go back to this point from the previous recursion, and then it back prints. So
I'm just waiting to go through the board.
yeah,
The system print out, it's going to be n plus n, n plus r.
I think so.
so if you so
Well,
this, what
concatenation.
you've got here,
I think
you can
concatenate
think of
rather
as
than-
inductive rules, because it's saying,
I'm trying to think
these are the
concatenate
starting
rather than
points,
adding, not like
and this is how I build up from my
So
starting
that's
points.
the
Whereas with the recursion, we're effectively
Basically,
starting at any
in binary.
given point and working our way
That's one thing.
backwards. So
This is n,
in
n
this
is 0.
example, we
So you do
are
3, it's got to be 11.
timesing by 2.
Yeah.
But note here, we're
You
dividing
do
by
one.
2.
Yeah.
Do 5.
So in actual fact,
So
you don't
we're-
need to necessarily worry too much about this.
There's 2 in there, so there's twice, doesn't it? Basically, 2, 2,
Which value is it?
1.
So what was it? 5 in this?
So do 5 divided by 5, basically 5 times is 2 going to 5.
Are you saying N or M?
Twice, was it?
No.
Nick or Mike? Nick. Right, okay.
Go right like that.
And then
Um,
zero.
So you've got N
1,
there.
So you divide by 2,
You've already, if you were to put
Yeah.
N in there,
and then you do 1.
then you would exit,
No,
you would
2
recurse with
remains
exactly
1.
the same value as what you started with.
So 2 divided by 2.
So you would never actually terminate. That would give you an infinite loop effectively. So M and R are giving you 2 new variables where you reduce the value.
Binary,
So you're constantly divided by 2. So if you
Last
put
year.
M in there,
I did access to
then
IT last
this
year.
value is getting smaller to the point where eventually this condition will be satisfied. Because eventually it will become zero.
Bring the remainder backwards, actually, no?
Yeah.
Well, you
So
said
then,
that was it.
once it's got to 0, 1,
I don't know why I did
then
it.
this function terminates, then it can jump back to this point from the previous step. And what would you say to the print
It's fine, cut this everything out.
Just yeah, absolutely. Spot on.
Might take a bit longer, so you can give us all back in it. 2, 3, 4, 5. Print bins, N.
Yeah.
Excellent. That looks about right to me. Yeah, excellent. Okay, so should we just have a quick recap on question 1 and 3 then? I think most people have managed to do these, which is excellent to see. So, question 1 is asking why must the is palindrome method going to terminate? So, who thinks they know this one? What would you think for question 1? I know you know it. Go on.
If the string reaches a length of 0 or 1, then it's over.
Yeah. So if it reaches a length of 0 or 1, then it's going to be able to terminate. So how can we be sure that it's going to reach a length of 0 or 1?
And that would only be after it's checked that we've given, and it gets short. It takes the remainder of what we take. And if it fails from the test, then it comes out anyway.
Yeah, so the fact that we could start with a string of X characters, 10 characters, whatever we may decide, but the fact that we're taking one character away from the start and one character away from the end, and then we call the recursion with that new string, means that eventually, as we keep reducing the length of this string, we'll get to be the case where it's 0 or 1, in which case it can terminate. Yeah?
I have backwards logic for that. I was like, if it doesn't end, it's going to crash.
If it doesn't end, it's going to crash.
Never mind.
If it didn't end, then it probably would crash, yeah. But so
Continue feeding a constant number of
Yeah, exactly.
yeah. But the point to think about is that no matter what the input is, it could be, in theory, it could be a string of 1 million characters, but it's going to be constantly taking one from the start, one from the end, and constantly reducing it. And so the fact that it's recursing on itself, so running the function again, but with that smaller string each time, then it will eventually get to a point where it can terminate. Of course, with the palindrome one, it's also looking at, is it a palindrome? And if it finds that the first and the last character don't match, then it's not a palindrome, in which case it will exit the method as well. So we can basically see that given any input, we work our way back to a particular base case where we can then say whether it's true or false to whether it's a palindrome. Okay? So can you see how that links back to the idea of induction? The fact that with induction we started with a base case and worked up, and with recursion we kind of start at any point and work backwards. Yeah? Excellent. Okay. So now, if we look at question 3, so we have this function, and what we want to be able to say is, given an integer, so given an integer, for print bin, we want to print out the binary equivalent, okay? So, just as before, we need to think about what the kind of base case would be for this, and then what the rule should be for all cases above that. So, if we've got n less than 2, then we're going to have n equals 0 or n equals 1, okay? So, with that in mind, what do you think we'd print for the character here? N? Absolutely. So we could just put the variable n into these brackets to be able to say, if we say print the binary value of 1, we know it's just going to be 1. Okay? If we've got a value where n is 2 or greater, then we enter this else statement. And in the else statement, we're saying, okay, we want two new values, m and r, where n divided by 2 is equals to m. And bear in mind this is casted to an int, so it's integer division. And n modulus 2 is equal to r. So we've created these two new variables now. And then the code suggesting that we're going to do a print bin method inside the print bin method. So this is our recursive step. So what do you think we might put as a new variable in print bin? Any thoughts what would go in print bin here? M, absolutely. So, what's happening is that we're constantly reducing n and then calling the method again using this new value. So, let's just write out an example on the board. So suppose we called it with the value 5, okay? So if we started out where n is equal to 5, we know we're greater than 2, so we go into the second part of the if-else statement, and we could say, okay, m is 5 divided by 2, which in the case of integer division is going to give us a 2, and r, 5 modulus of 2, 5, so what's the remainder? The remainder here is going to be 1, okay? Now, if we put m into that bracket so that we do this recursive call, then effectively we take the value here and we go into a new step of running the method. So now n is equal to 2. Okay? N is equal to 2, and so if n is less than 2, we go into the first bit. In this case, it's not, so we go into our else again. So we compute m to be 2 divided by 2, which is going to give us a value of 1, and we compute r to be 2 modulus of 2, which is going to be 0. Okay? Then recursion kicks in again, and we jump to another state of it. So we've called the function for a third time down here. And now we've got n to be equals to 1. At n equals to 1, we know that we satisfy the condition for the if statement, and so we can enter the system.out.println that we put in earlier. So when we say that to be n, we can just take the value here. So we'll print out a 1. Then what happens is that we jump back to this part of the method because we've entered it here and we've exited the method for that third call. So then we get to this print out, print line for this step in the process. So what do you think we might put in the brackets here? R. R, indeed, yeah. So, if we were to put R in there, then we've already used M for when we're doing recursive steps, and we can just take R to be the value here. So, if we've got R there, then we take 0 to be the answer there, we step back up to this part, and we take R again, and that gives us 101. Which is obviously what we're after. Okay? Can everyone see how we got there? Everyone happy so far? Yeah? Cool. Okay, I'll give you a little bit longer to look at 5, 6, and 7, and then we'll chat through that as well. You guys happy with everything discussed?
Oh, yeah.
Recursively call back to it. And also the A greater than B, it does say there's an assumption that that's already the case.
Oh, right.
So, but yeah, it doesn't necessarily matter if you looking back to that.
Right, okay.
Okay, should we look at question 5?
Please.
Yeah? Okay. So, with question 5, we've got this function called GCD, so greatest common divisor. Okay, and basically, what we're saying, we've got two numbers it can take, so int A, int B, so one example may be GCD 15, 6. And it's going to try and find the greatest common divisor for these. So in this case, greatest common divisor would be 3, because we can divide 6 by 3 and we can divide 15 by 3. Okay? Without leaving a remainder, obviously. Okay, so we've got a bit of a hint in the question here. And it says Euclid worked out a long time ago that if A is greater or equal to B, then either B is equal to 0 and the GCD is A, or it's the same as GCD B A modulus B. Okay? So, what we need to say is, as we've done before, an if-else statement. So we're going to say if something, do something else, we're going to do something else. Okay? So, what do you think we could use as a condition to go into our first part of the if-else statement?
B equals 0?
B equals 0, yep, absolutely. So, if we were to say B equals 0, then what would we be returning? A. Spot on. So, here then, as it says, so we know that A is greater or equal to B. As it says, assuming when the method is first called, A is greater than or equal to B. And it says then either B is 0 and the GCD is A. So B is 0, GCD is A, so we'll return A. Otherwise, it's this other bit. So what do you think we'll write here? GCD,
B would be A
modulus B. Yeah? Okay, so what we'll do is write return and then GCD B and then A mod B. Okay, so return GCD B A modulus B. Okay, so let's just think about that and work it through with an example. So we've got GCD 15, 6. Okay, so if we assume that's 15, that's 6. Remember, that's 6 really. So B is 6 and A is 15. Okay, so if B equals to 0, well, it's not, so we're going to go to else. Return GCD B A modulus B. So again, we could say here we've got 6, because that's what we know B to be. Then A modulus B, that would be 15 mod 6, which is going to give us, what would 15 modulus 6 be? 3. Absolutely. So, that gives us 6 and 3, which we then feed back into A and B here. Okay, so 6 and 3, then we can run through again. So we know that B is equal to 0 is not true. So then we say else, return GCD B A mod B. So here then we can say 3 and we can say 6 mod 3, which is equal to 0. Absolutely. Feed that back in. And then if B is equal to 0, return A, which we see to be 3. Okay? Can everyone see how we managed to work through that? Yeah? Excellent. Okay. So then, has anyone managed to get onto question 6? No? Okay, so we're getting close to time now, so what we'll do is just talk through what's happening in question 6. So here is we've got Pascal's triangle. So what Pascal's triangle is effectively starting from 1, we're saying for any given value in our triangle, we find that by taking the sum of the two values above it. So for instance, 4 is going to be 1 plus 3, 6 is going to be 3 plus 3, 2 is going to be 1 plus 1, etc. So this is a triangle which effectively is infinite. We can carry it on for as many rows as we want. And what the question's asking is, what is the Java function to compute Pascal's triangle? Now we've got this notation of C, where C has n and I as parameters, n being the row, and I being the index along the row. So, for instance, this value here, this 4, it would be 0, 1, 2, 3, 4, 1. So it would be C, 4, 1. Okay? Now, effectively, what's happening, if we also imagine we've got zeros in all the spaces outside the triangle, effectively what this function's saying is, if my index is -1, which would mean if I'm over here somewhere, or n is -1, which means I'm above it somewhere here, or I is equal to n plus 1, in which case I'm over here. So basically, if I'm out of bounds, return 0. Okay? If I is equal to 0, or n is equal to 0, which effectively, I feel like there's maybe something missing from there, because you could also say I is equal to n. I is equal to n. Basically, anything along here is going to be returning a 1. Okay? So this effectively gives us our base case, where we either have a 0 or we have a 1. And so if we don't fit into either of these, i.e. we've specified a row and an index somewhere in this space, or this space if we extended it, then effectively what we do is return the values of the two elements above it. So here then we're saying return C of n minus 1, I minus 1. So if I was here, that would be referring to this 3 to the top left of it. And plus that with n minus 1 I. So again, from this 6, that would be referring to this 3. So this will then propagate up through the triangle until it gets back to a case where we've got a 1 or a 0. Can everyone see briefly how that works? Any questions at all about how it works? So you can see again how we've used recursion to be able to search a space, to be able to populate the triangles. And what's interesting about this one is that before we've had a single function call back to itself, whereas here we're now spreading that out so that we've actually got 2 recursive calls. So as you build up more and more levels to this triangle, you're going to have more and more recursive calls backward to it. Okay. Any other questions on recursion?
Is it going to be on backward?
Yes, I'll make sure the slides are available for you so that you can have that. Any other questions? Or? No? In that case, thank you very much for your time.
Not sure what you're going to be doing it. Internet?
Yeah.
Google it.
That's what I did.
Did it work?
For the first one, yeah. So like how to
That's why I like
I haven't attempted the question 4, 5, and 6. Those ones I think
looked at me. One of the things, if you don't submit it, you don't get